Hello everyone and welcome to Chapter 2, Three-Phase Induction Motor in the Three-Phase Induction Machine course. In this chapter we are going to cover the three-phase induction motor construction and terminals connection, and we are going to look for the slip concept, theory of operation, and per-phase equivalent circuit. Once we finish this chapter we will understand the construction of a three-phase induction motor, and we are going to demonstrate a strong grasp of the theory of operation. We are going to delve more in the theory of operation. Then we are going to differentiate between the two types of the induction motor, squirrel cage and slip ring induction motor. We didn't understand what do you mean by squirrel cage and slip ring. We are going to cover that one through the chapter, no worries. And then we are going to demonstrate the ability to wire the motor on both star and delta connections, or delta star and delta configurations. I presume that you covered the review chapter and you look for the three-phase winding. So you know what I mean by star and delta connections. Then you are going to assimilate the concept of slip speed, which is a very important concept for this machine. And after that one, we are going to derive the equivalent circuit from the theory of operation. As usual, each chapter consists of a group of videos. So in chapter number 2, video number 1, we're going to have highlight about induction machine. Then we are going to look deeply for the machine construction using slides and live demos. And we are going to end up this chapter by a group of questions from industry employers they use during the interview sessions. We are going to start by the classification of electrical machines. So electrical machines can be broadly classified into rotary machines and linear machines. So linear machines such as linear motors used for maglev trains. But rotary machines can be classified into two types or two main types, conventional machines and special machines. So special machines such as switch reluctance motors, stepper motors, or any permanent magnet motors. But conventional machines can be classified into three types or main types: DC machines, synchronous machines, and asynchronous machine. DC machines and synchronous machine will be different courses, but we are concerned by asynchronous machine. Asynchronous or induction, we are in induction machine course, so both words can be used. So induction machine, we call it induction machine because of the induction action inside the machine itself. But we can use the word asynchronous. The stator is running by synchronous speed, while the rotor is running by different speed, and this is why we call it asynchronous. For example, MATLAB didn't use the word induction machine, they use asynchronous machine. But we are going to use both of them, in asynchronous or induction. So before we start the induction machine or asynchronous machine, we are going to look for some concepts for those who didn't watch chapter number 0. If we have a conductor with certain length L, there is a flux density B applied to this conductor. And this conductor is running by relative speed, where this speed is the speed between the conductor and the field in meter per second. There will be induced voltage E equals BLV relative. If V relative is 0, this induced voltage will be 0. And if there is a current I going through this conductor and there is a flux density B applied to this conductor, there will be a force F equals LIB. And force multiplied by distance can give you torque, so torque is function of this flux and the current I. Also, to have a torque in electrical machines, you have two types of torques. One of them we call it saliency torque, where torque is proportional to the rate of a change of the reluctance with respect to the position. And another type where we are going to look for, this is an induction torque. Torque is proportional to two flux and an angle between them. So here in an induction machine, we have flux in the stator and flux in the rotor, and there is an angle between them. So torque is proportional to phi1, phi2 sine theta. And we call it induction torque, and this is why we call it induction machine. Some highlights about induction machine or asynchronous machine. Once Nikola Tesla promoted the concept of alternating current in the 19th century, I'm not here going to speak about the fight between Nikola Tesla and Thomas Edison, but once he promoted the concept, he used it to produce a rotating magnetic field we explained in chapter number 1. Then he invented the induction machine and patented that one in December 1889. From this time up till now, Induction motor account for over 90% of the total energy consumed by electric motors. So why the induction motor takes this privilege? Why? We need to answer this question. Let us list some advantages of induction machines compared to other machines. For example, single source with winding structure flexibility. What do you mean by single source? The machine is only fed from single phase supply? No. So the machine has a stator rotor like any other machine, but the supply is only from the stator side. While a machine like DC machine or synchronous machine, they need a source in the stator and another source in the rotor. So advantage here, or the advantage of the induction machine here, single source from the stator side. So what do you mean by winding structure flexibility? So if we have a certain number of slots in the stator, we saw that one in chapter number 1 before, so we can wind this machine by different number of poles, and also this machine can be fed from either single phase source or 3-phase source, or we can elevate that one to something like 5-phase source. We're going for multi-phase machines. So the flexibility here for the number of poles you can furnish your stator or the source you are going to apply to this machine. Based on the research papers and industry employers' feedback, the machine is rugged, reliable, relatively inexpensive, and easy to maintain. What do you mean by easy to maintain? So some other machines, if there is a problem happen in the winding, so they need 1 month at least to rewind the machine. But induction machine maximum needs 3 days. It's easy to rewind the machine. This is just a quick example. And easy, you are going to return back that one, and quickly you are going to return this machine to the production line, and you are going to have a cost effective here or saving cost because the production line is going to run again quickly. Also, the machine has rating starts from fractional horsepower in the level of single phase up to tenths of kilowatt and above for 3-phase. And the typical efficiency is more than 90%, and nowadays we can reach more than 95%. Also, in some special industrial application, the machine has a high rating, reach up to 500 horsepower, something like mining applications or fans for mining applications. Another advantage of this machine that the machine has no brushes, so it can operate in hazardous areas, something like oil and refinery applications. But someone can say that I'm not agree with you because a slip ring induction motor has brushes. You are 100% correct. I'm not speaking about slip ring induction motor here. I'm speaking about squirrel cage. So we are going to look for the difference between a squirrel cage and slip ring when we are going to cover the construction slide. But here I mean squirrel cage induction motor. The application for these machines are huge, are too many. The main applications are pumps, compressors, packaging, printing, fans, air conditioning, transportation, and production such as lathes and rolling mills. Also, this machine can be used as induction generator in wind turbine applications. So what is the induction machine construction? Look into this picture. We have stationary part and rotary part. So the stationary part is represented by the stator. So the stator includes here the frame, and also we have the stator winding. The stator winding will be connected to the terminal box, and then we can add to the frame the nameplate where we can find the information about the machine such as rating and performance. Also, eye bolt here can be used to lift the machine. In the rotor part, we have a shaft connected to the rotor. The rotor will be fitted inside the stator, and there will be a shaft here, but also in the rotor, we have in this side what we call it the bearing. The bearing will support the shaft and allow smooth rotation. We have other parts, something like housing, fan and fan cover here, and also we can have end cover. So in the next slides, we are going to look for the stator rotor in details, but also we are going to have a real machine. We are going to look for these parts live. We have here a 3-phase induction motor, resembles what we explained in the previous slide. So as you can see here, we have the stator frame. So the stator winding will be inside, and there will be the rotor, and the rotor shaft will be inside the stator. This side is the mechanical part. So this machine could operate as a compressor or a pump. And this side is the machine cap for the fan. And that one is the terminal box. And as we can see here, we have the nameplate of the machine. So the question now, how do you know that this machine is a 3-phase? So I look for the terminals, but that one is not clear enough because I have here only 3 terminals, and I expect for this machine to have 6 terminals. We have 4. That one is the ground for the body. So we have phase A, phase B, phase C. So that one is a 3-phase machine. But I like to confirm. So to confirm that one, I looked for the nameplate and I read in that one 3-phase motor. I'm going to speak about the nameplate later, but now I'm going to open the terminal box in front of you to see what's inside, and the end cap cover or the fan cover to see how the fan is fixed to the shaft. And also are going to look for the stator and rotor in details for another machine I dismantle it to see what's inside. As we can see here, this is a fan connected to the motor shaft here to rotate with the shaft. And also I'm going to open the terminal box now. So once I open the terminal box, I can see that this machine can be connected as a star or delta. So let me make it clear for you. That one will be the star connection. If we connect these 3 terminals together and feed the machine from 1 to 3 or ABC or UVW, whatever. But if you like to connect the machine as a delta, and now the machine is connected as delta, you are going to connect this winding by this winding, and this one by this one, and this one by this one. And also you feed the machine from these 3 terminals. So it's clear here we have 6 terminals for this machine, but I'm going to look for the nameplate or later on and the terminals for the dismantled machine, and we're going to speak about that one in details. So let us look through the stator in details. The stator consists of laminated sheet steel or silicon steel laminations to reduce the eddy current loss. If you remember from the previous chapter, we have the rotating field theory, that the rotating field is function of time. So we need the lamination here, like what we can see here, to reduce this eddy current loss. When these laminations are punched and stacked together, they form the stack length. We call it L. If you remember the equation E equals BLV, this is L, the effective length of the machine. So I use here the wooden model I did, but that one should be iron machine. Once you are going to have that one or this stator core, you have what we call it slot and tooth here. So you form now slots and teeth for this stator core. So the stator core now is going to be furnished by the coils, and the coils are wound using copper or aluminium. So we are going to furnish that one based on what I explained in the previous chapter. So you can form this machine as 2-pole, 4-pole, 6-pole, 8 poles. So it depends on the number of slots you have, and then you are going to find the number of slots per pole, the number of slots per pole per phase, and then you are going to see what is the start and finish for each winding. So you end up by 6 terminals in this case. Once we furnish this machine, we are going to have something like that one. The machine here we can have is North Pole, South Pole, North Pole, and South Pole. This one is 4-pole machine, and we have here something like slot and teeth. So as you can see here. But before we're going to end the machine or cover the machine, we should make some installations here, and we make sure that the terminals of the machine, or using the measurements, something like mega, to measure the resistance between the winding and the stator body, that one should be something like mega ohm. So to make sure that there is no short circuit between your winding and the stator body. So definitely you have something like the nameplate on the top of this one. So here we have the insulation applied, and the windings are connected now to the 3-phase supply to have the rotating field we explained before. Here we have another machine similar to the one I showed to you before, but I removed the end cover from both sides. So we are going to take the rotor away now. So we'll put the rotor away. I'm going to return to this rotor later on. As we can see here, we have the stator consists of slots and teeth, and these slots are furnished by 3-phase winding. So we have here in the terminal box 6 terminals for the phases A, B, C. We're going to return to this terminal box later. But now we look here, we have a North Pole and South Pole. So this machine is a 2-pole machine. So what would be the case if I didn't know from the winding arrangement that that one is a 2-pole machine? And usually that you cannot open all the time the machines to look for the winding from inside. So you need another method or alternative method to know the number of poles. So I'm going to look for the nameplate here. So the nameplate tells us that this machine can be connected delta or star. So for delta 220 volt, for the star 380 volt, and the frequency is 50 hertz. And also you can have the power, which is 0.55 kilowatt, and the speed, which I need to know, 2750 RPM, and give you the currents. I'm not going for everything written here now, so we are going to discover that one bit by bit, but now what I need is the speed. So we can make some calculations now. So if we have the frequency 50 hertz, and the rotor speed, the rated value, 2750 RPM. So the number of poles can be calculated from the equation we had before in the chapter number 1, NS equal 120 Fs over P. So I'm going to assume that the rotor speed is similar to the synchronous speed or the same value. So I'm going to substitute in this equation 2750 RPM equal 120 multiplied by 50 hertz over the number of poles P. So we can calculate that one here using this calculator. So that one will be 120 multiplied by 50 over 2750. So that one give you something like 2.18. So we know that the poles should be even number, integer number. So either we are going to choose 2 or 4. So someone said that I'm going to choose 4 poles. So that one will be speed, synchronous speed equal 120 50 over P, which is 4. That one give you 1500 RPM. So the rotor speed is more than the synchronous speed, and that one is not accepted. Now we are going to discover that one in the next video about the slip speed concept. So we need to have rotor speed is lower than the synchronous speed. So we are going to choose P equal 2. So NS equal 120 multiplied by 50 over 2 give you 3000 RPM. So the synchronous speed is 3000 RPM. So now we are going to say that the number of poles of this machine is 2 poles. Let us apply the same concept for the other machine we have. So this machine is a 3-phase motor. For 50 hertz supply, we have the rated speed for the rated voltage and frequency 1390 RPM. So for the frequency 50 hertz, the speed 1390 RPM, the number of poles will be 4.31 if we assume that the rotor speed is the same like the synchronous speed. We need the number of poles to be integer, even number, so we are going to choose 4. At that time, NS equal 120 multiplied by 50 over 4 give you 1500 RPM. What about the rotor? This machine has 2 types of rotors. One of them is called the squirrel cage, and the other one is called slip ring or wound rotor type. So both names are correct for the slip ring or wound rotor type machine. So we are going to explain them one by one to see what is the difference between the squirrel cage and slip ring in the next slides. Let's start by the squirrel cage rotor. The squirrel cage rotor is manufactured identical to the stator or similar to the stator from laminated sheet steel. So you can see here there is one of the laminations. When we are going to stack these laminations together, we form the rotor body with effective length L, where E equals BLV. So this is the effective length in the EMF equation. When we stack those together, we're going to have slots in the outer surface. These slots will be filled with conductive rotor bars. So the rotor bar or the conductive rotor bar could be from aluminium or copper. This one is a rotor bar. And as you can see here, that one here. So they are distributed on the periphery of the rotor. Right. So how we are going to add these bars? So using die casting process or directly cast into the rotor core. So the die casting process is the metal is molten and injected in a high pressure into the slots. But now we have a certain number of bars distributed to the rotor. And how to know or to calculate the number of the rotor bars? Here in this video we are covering the construction, not the design. So that one will be later on. There is a certain formula you can calculate the number of rotor bars. So when we are going to have these bars, we are going to connect them by what we call end rings. We are going to make a short circuit in both sides for the rotor bars. So that one is the end ring, that one is the end ring, that one is the end ring, as we can see here. So those are end rings, short circuit all the rotor bars. We notice now that there is no external power supplied to the rotor, so the rotor is closed on itself and we cannot access the rotor terminals. In the classroom, the student asks a good question all the time: why the rotor bars are skewed? So this is a good question, but that one is a big story that need a different analysis. But quickly we can say here that skew bars is deliberate. We needed to reduce the cogging torque and smooth the interaction with the field and minimize magnetic lock. That one is reduce harmonics and improve starting performance. So in summary for that one, why we have this skew, that one to improve the performance and avoid any cogging torque at the starting. But there is analysis we can add to know how to know the skew angle and so on. Back to the real machine we have here. That machine is a stator, a rotor. I'm going to take the rotor out and move the stator aside for not confusing us now. So this is the rotor we have, and this is another sample of a rotor. And this is the laminated sheet steel we have. So if we have these laminated sheet steel, stack them together, they form this rotor as we can see here. So we have the slots, and we are going to add the conductive rotor bars here. So looking for that one, but we notice here we didn't see any bars, but we see the laminations. So if we look deeply here, we are going to find that the slots or these bars are on the surface. So these are the slots as we can see here, and these are the conductive bars. And from the other side, you are going to see the conductive bars here, and they are in some slots. And they are straight line, they are not skewed. And we have here end rings from this side and another end ring from this side. And we have bearing from the left side and bearing from the right side. And for the other rotor we have here, we have aluminum bars, as you can see here, 1, 2, 3, 4, 5, and so on, distributed to the periphery of this rotor. And we have end ring from this side and another end ring from this side. And this is a rotor shaft, definitely. Two questions here. We notice for this motor that the bars are straight, it's not skewed. So we should skew that one. Not all the motor are skewed bars, because this motor is 0.55 kilowatt. When we need a high performance, we need to skew these rotor bars. So in some motors you can find them not skewed, just to make the construction or manufacturing is easy, because skewing the rotor bars is complicating the manufacture process. This is question number one. Question number two. How do you know the number of poles from these rotor bars? It's not clear to me that one is a North Pole, South Pole, North Pole, South Pole. Actually, the privilege or the advantage of this machine, that this machine is adaptive. So the rotor of the squirrel cage motor is adaptive to the stator. So if you have a stator, single phase stator, so this machine is going to operate as a single phase. If you have for the same size 3-phase machine, that one is going to operate 3-phase. If this machine is 5-phase, this rotor is going to be 5-phase. Regarding the number of poles, if the stator is 2-pole, this rotor is going to adapt itself to be 2 poles. If the stator is 4-pole, 6-pole, 8 poles, the rotor is going to adapt itself to match the stator. And this is one of the big advantages of this machine. Back to the other rotor type, slip ring or wound rotor. So it's manufactured identical to the stator or to the rotor of the squirrel cage motor, using laminated sheet steel, and there will be slots formed on the surface of this rotor. So what is the difference between the squirrel cage and slip ring type? So the slots are furnished with copper winding for a specific number of phases and specific number of poles. It's not like the squirrel cage we have rotor bars or conductive rotor bars. Here we have a specific number of phases and poles. So we furnish that one using the 3-phase winding technique. And we need to apply the conditions that each pole should accommodate all phases, and the phase displacement between adjacent phases 120 degree electrical, and the start and finish between the same phase will be 180 degree electrical. So the winding are connected star and internally connected, so definitely we have 3 terminals out. So look here for this rotor, we have this rotor and we have 3 terminals. So how to access these terminals? The rotor now is accessible. We can inject or collect or maybe short circuit that one, similar to the squirrel cage, by short circuit these terminals. So to access these ones, we need slip rings. So these three terminals from the rotor now will be soldered or braced to three slip rings. So that one is a slip ring number 1, number 2, number 3, and they are rotating with the same shaft. So what is the difference between soldering and brazing? Both are metal joining techniques, but solder is used for low performance machine and braze should be used for high performance machine. So brazing will be used for high temperature, I presume more than 450 degrees, and use harder alloys. So now we have three slip rings. How to collect, how to inject. So we need to have carbon brushes connected to these slip rings, as we can see here. So these are the carbon brushes and carbon brush holder, right? So they are connected to these three slip rings. So before we leave this slide, so why this motor is called slip ring? Because we have three slip rings here. And why some people call it wound rotor? Because we have the winding construction here, three-phase winding. Before we conclude this slide, definitely insulation is required, and as you can see here, varnishing that one will be an important issue to make sure that there is no inter-turn short circuits. So in conclusion, slip ring or wound rotor type will be rotor three-phase, match the stator number of poles and number of phases. It's not like the squirrel cage. The squirrel cage, the rotor can adapt the stator. Exercise number 1. Some industry employers ask this question during the interview process. We have two three-phase induction machines, machine A and machine B. Both have the same power rating. One is a squirrel cage type and the other is a slip ring type. Based on physical inspection, how can you distinguish the squirrel cage machine from the slip ring machine? And they give us a note, nameplate is not accessible. So you cannot read the nameplate and say this machine is a squirrel cage, so the other one is slip ring. My suggestion to you now, stop the video and try to think for an answer to this question. Let me remind you, this button is not active. I presume you found an answer for this question, so let's resume the video and try to find a correct answer for this question. So some people say that I'm going to open machine A and look inside that one and look for the rotor. If it's squirrel cage, so the machine A will be squirrel cage and machine B will be slip ring. But that one is not accepted. During the interview process, they didn't give you the time to open the machine to check what's inside. And also nameplate is not accessible. So what is the solution? If you remember from the machine construction, the squirrel cage has conductive rotor bars with certain length L. So the machine has certain effective length L. For the same power, slip ring motor should have the same effective length L as well, but the shaft has another or extra 3 slip rings connected. So this means the shaft of the slip ring should be longer than the shaft of the squirrel cage. So if the squirrel cage shaft has a certain length L, so the slip ring one will be L plus. So as you assume that the squirrel cage one is 30 centimeter, so the slip ring will be 35 centimeter. So there will be extra length here due to the slip rings added to the shaft. So by your eye, you can say that that one is a squirrel cage because that one is shorter shaft, and that one is slip ring because that one is a longer shaft. Let's ask another question. But that one I didn't add it as another exercise. Why some machines are red color and other are blue colors? So it depends on the manufacturer, but usually the blue color is used for normal applications like fans, blowers, compressors, normal pumps, but the red color is used for fire pumps. So to distinguish between the fire pumps and any other application, sometimes they use the red color. Let us take another exercise from industry employer questions during the interview process. we have two three-phase induction machines with the same stator size and number of slots. Machine A is a four-pole squirrel cage type, while machine B is a two-pole slip ring type, as shown in the figure. The question is, can we put the rotor of the squirrel cage in the stator of the slip ring machine and vice versa? So my suggestion to you again to stop the video and try to find an answer for this question. I expect now we can resume the video and then try to find an answer for this question. If we have squirrel cage rotor, as we explained before, the squirrel cage rotor can adapt itself to the stator. So if the stator is single phase, the rotor will be single phase. If the stator will be three phase, the rotor will be three phase. If the stator is two poles, four poles, six poles, the rotor is going to adapt itself. So you can take this rotor and put it in the two-pole stator and there is no problem at all, and that one is accepted. But when we have slip ring rotor, that one is wound as two-pole to match its stator. So that one is a two-pole as well. So the rotor is two-pole, three-phase two-pole. So cannot work for any other stator other than that one. If we take that one to put it in a four-pole machine, that one will not be accepted because the machine now has a stator, four-pole, and rotor two poles. Another exercise from industry employer questions during the interview process: compare squirrel cage and slip ring induction motors. The comparison should highlight both similarities and differences. I'll leave for you this question to answer. If you watch the video and the previous slides, you can answer that one easily. But also, when you watch next videos, you can enhance the answer as a face of comparison between squirrel cage and slip ring. Let us summarize this video. We had highlights about induction machine. We looked for the construction of the induction machine in general, guided by live demo. I brought for you a real machine and one of them is dismantled, so we looked inside the machine. We looked for the stator construction in details, the construction of the squirrel cage guide motor or rotor guided by live demo as well, and we looked for the detailed construction of the slip ring induction motor, and we ended up this video by some challenging interview questions about the induction motor construction. What will I watch in video number 2? So chapter 2, video 2 will include machine terminals and slip speed concept. See you in the next video.